again. We are very pleased to have our first speaker today, Slawomir Solecki, with us here at our conference. The title of his talk is rather tantalizing: Compact Spaces and Logic.
I'd like to thank the organizers for the invitation. It's really nice to be here, especially in this weather. I have a woolen cap that I brought from home to my closet. It looks more and more surreal there. The weather is so beautiful. It was snowing when I was in any case, so what I want to talk about is, well, it comes from an observation. The observation is made a long time ago, but somehow the validity of this observation had to be checked. So it took some time to actually work out various examples that are test the validity of this observation. So let me talk about. So what I want to talk about is this projective Fraisse method. So I will start just with explaining what Fraisse limits are. This is a method coming from model theory. It's a method of constructing, sort of generic method of constructing countable structures. So discrete countable structures. And then what we'll do, we'll reverse all the arrows in the construction. And this will no longer construct. Now we'll run essentially the same argument. What will happen is we'll not get anymore a countable discrete structure, but because we dualize, we'll get compact structures. And then these structures will have always an equivalence relation on them. So the structure itself will not be so interesting because it will, the underlying set will be just a counter set. But it will carry a natural equivalence relation, compact. We divide by it and then we get interesting topological spaces that are no longer zero-dimensional like the counter set. And the equivalence relation, this sort of combinatorial encodes information about the space. So then we can trade topological problems for combinatorial problems, and this is very much makes the problems much easier often. So, and then I'll have some examples of applications that have been done in the past, and then I'll illustrate things on points 3 and 4 if I get to 4. So on the Menger curve, and then on simplexes, which are sort of the simplest higher dimensional objects. So this is something that was 2, 3, and 4. It was something that was done recently. Okay, so what is our aim? It's to develop model theoretic combinatorial sort of point of view and find canonical combinatorial models for compact topological spaces. Maybe all. By compact I mean second countable compact here. So I don't want to keep saying that. I'm not saying that only second countable spaces are interesting, but in this talk I cannot handle any other spaces. So when I say compact space, I mean second countable compact space. So we are also, what this gives, for example, is a unified approach to topological homogeneity results. So essentially, if you want to prove homogeneity, you have a space represented in the way that I'm talking about here. There is one way to go, and then it either works or it doesn't. So I will say a little bit about, more about that. We get some form of homogeneity for free, what I call projective homogeneity. But most often, topologists are interested in the dual version, direct homogeneity. So then there's a lot of sort of combinatorial work that one needs to do to flip this arrow, go from projective to direct. But I will not get into details here. And then the idea is to connect it with descriptive set theory, Ramsey theory, and topological dynamics. So this is the usual thing that one would want to do when one deals with Fraisse limits. So one would now want to connect, say, study topological dynamics of homeomorphism group of these spaces using its dense subgroups that come from this representation that I did. So these are some of the aims. So just to give a picture, so in essence, it's replacing studying things of this sort. This is the browser, right? So you've got the counter set, and you have the semicircles up, and then smaller semicircles on the left-hand side. So this is real life. And we replace it with static things like of this sort. So this is just sort of combinatorial little graphs. Okay. So what is this method? So let me talk first about direct Fraisse method. So this is a method coming from Fraisse from the 50s. So what I have is some class of finite structures. So countable class of finite structures. So I say fix a language. This means fix the type of structures that you have. For example, you have graphs, or you have linear orders, or maybe you have groups. So you fix the type of structure that you want. Fixing a language means you say, okay, I'm only interested in relations of this sort, relation R1, R2, R3 of this and this array. You can throw in functions if you want. No problems with that, even though this will not show up. I mean functions symbols will not show up. Okay, and I consider these finite structures with embeddings. And they consider with embeddings. Okay, and then such a family is called a Fraisse family if it has joint embedding property and it has the amalgamation property. That's the more important of the two. So amalgamation property is as follows. If I have B1 and B2 and A all coming from F and A embeds into both B1 and B2, then I can amalgamate. It's the only thing that's required. So I can find a structure C again in F such that the diagram commutes. So structure C and embeddings of B1 and B2 into C so that this whole thing commutes. So I can glue together B1 and B2 over A. That's joint embedding property looks like a special case of this. Joint embedding property means simply that given without A, given B1 and B2, there is a C to which I can embed both B1 and B2. This is because we don't allow empty structures. This is joint embedding property is not a particular case of this. But joint embedding property is usually trivial to check. This one often requires some work. Okay, so amalgamation property. And then what Fraisse noticed is that if you have a class, countable class of finite structures of this sort, then there exists, you can take the limit of the family. So there is a unique countable structure that can be, so the structure is unique up to certain properties, that can be considered the limit of the family. So you, in essence, the family has a unique infinite structure that's behind it. And so in essence, what is going on, we take F and we produce a sequence. Out of F, we produce a sequence that is as generic as possible. And I will give some details later on when I talk about this projective thing. So in any case, there is a unique countable structure like this. So let's do two examples. So first of all, this is the most classical example. So I have a family, you look at the family of all finite linear orders. You check that linear orders do have this amalgamation property. It's easy to check. So this is a Fraisse family. It's a countable Fraisse family because there's only countably many finite linear orders. So there is this limit. And one can look at the limit and identify it as the, well, what else would it be? It would be the rational numbers with less than. This is the generic countable linear order. So it turns out that the limit of this family is exactly this structure. And then one can do something different. For example, look at the family of all finite graphs. Again, it's a countable family. There's only countably many finite graphs. Amalgamation property holds. Just check it by hand. So it's a Fraisse family. So there is a limit. Well, if you think of what is the most generic graph, countable generic graph, it's the random graph. So this is maybe an object that is a little less known. So a random graph can be, for example, so the usual way one defines it is you look at natural numbers and then for each pair of natural numbers you flip a coin. So if it comes heads, you draw an edge. If it's tails, you don't draw an edge. And then you do it independently for each pair. And then with probability 1, you get the same object. And this is the graph. So, and then there are many more objects that are constructed this way. For example, there is the so-called rational Urysohn space, from which you get the universal metric Urysohn space. So it's also in a natural way a Frey cell limit of this sort. But now, so these structures that we are getting here are all infinite, but they are discrete. Count. Okay. So what we do, we will dualize the whole construction. So we again have, so let's just say what's the difference. So what we do is we still have a family of finite structures and we take it with epimorphisms now. So not embeddings, but epimorphisms. So bonding maps will be, I have two structures, has to be a surjection, has to preserve all the structures. So if it's a group, it's a homomorphism. If it's a graph, it should preserve the edges. But it also has to be on relations, in the sense that if something in the image, some tuple is bound by a relation, is part of a relation, then it has to come from some tuple in the domain that is also part of the relation. So epimorphisms, unlike embeddings, and then we have joint epimorphism property and projective amalgamation property, which is the same as before, except that we changed the arrows. We flipped them. So given B1, B2, and A, and arrows, so epimorphisms from B1 and B2 to A, we can find the C also in F, and epimorphism to B1, B2, so that this diagram is commute. Now, okay, so let me just say right away, because it will come out with examples, so I cannot hide it. So often, this F, I say, we often do not take, we take a class of structures, and most often you will not take all epimorphisms. You take subcategories. So you take a subclass of epimorphism closed under composition, and you require this for it, this amalgamation to hold inside of this category. Often this subcategory is really done by, you start with some class and then you simply add new relations to the class. And then this limits the epimorphism that you have. But in general, this cannot be done this way. Okay. So let me just say exactly, so one more time. So we start with a class of finite structures and epimorphisms. We close it under inverse limits. So we take finite structures, epimorphisms between them, we take the inverse limit. About the inverse limit, unlike in this discrete case, we remember the topology. The topology is trivial usually, but we do remember it. So it's a compact zero-dimensional topology. Most often you get actually the counter set, but sometimes not. But it's always zero-dimensional and compact. Now I assume that it's a projective Frey family, so I have this diagram always holding. And then I am able to construct, just like Frey did, so we did it with a student of mine, Erwin. So we constructed a generic sequence inside of this F. So generic sequence means so assume you've constructed the sequence up to n. Let's say up to some point. Let's say somewhere in the middle. It's not in the picture. Somewhere in the middle, and then a structure B is presented to you with an epimorphism coming to a structure that precedes the one, maybe it's your structure, the last one, but maybe some earlier structure. Then what you have to do is you always have to find a structure later in the sequence and an epimorphism to B that will close this diagram. So somehow these sort of arrows coming here present challenges to you, and you have to meet every challenge. And you will meet every challenge infinitely many often. So essentially what happens is everything that can happen happens infinitely many times. There is no restrictions on the kind of, say, no restriction on what maps to take here in the sequence. Essentially you take all possible maps in an as unorderly fashion as possible. So in this sense the sequence is generic. Okay, so now and then we take, of course, the sequence, a finite structure, take inverse limit. This is a zero-dimensional compact space, but it carries additionally this model theoretic structure. So there were relations here. These relations will be inherited by the limit. So if there is some graph relation, this will be a graph. If there is some functions here, there will be functions here. So just to capture what's going on here in this limit, I would say that M, so this is like the structure in the picture, is a topological F structure. F is my family. topological Fs, what do they do? If it's compact, zero-dimensional, each relation symbol, so these are the symbols in what I call this language, each relation symbol is interpreted as a closed relation in M. It may have high arity 3, 5, but often it's binary. And F is, so this is essentially the last point says that M is the inverse limit of elements of F. So this means if I have any continuous function from M to X, X a finite space, so essentially this is just a partition of M into Clopen sets labeled by element of X. It will factor through an epimorphism from M to A. So if I have M, I'm going M, oh, this is worse. Okay, it is what it is, I guess. We are doing this, okay, X. Wow! There's a conspiracy here. Let's see. Okay, in any case, this is what's happening, right? If you have this, you can factor through. So every continuous, every finite partition factors is refined by an epimorphism. Okay, so then the theorem that we prove is there is a unique topological F structure, like on the previous slide, provided I am starting with a projective Freyset family F, and it's countable. So there is a unique structure F with the universality property. So for every A in F, there is an epimorphism coming from F to A. So epimorphism means there is a continuous function. F carries this topology. A continuous function from F to A. A is finite, so discrete topology. There is an epimorphism, just like I explained before. It respects all the relations. Now, if I'm cutting down to a subcategory, this is a little. I have to be a little more careful to be able to define what I mean by an epimorphism in my class from F to A. It's not given, but it can be done. If I take all epimorphisms, there is no problem. And projective ultrahomogeneity. So this is a homogeneity with all the arrows flipped. So if I have F and I go from F to the same structure A by F and G, then I can permute F by an automorphism and close the diagram. So any two epimorphisms from F to a structure in script F are essentially the same, meaning there is a homeomorphism of F that preserves all this additional structure that will make F go to G. So this is a projective ultrahomogeneity. So these are, if people know Freyset limit, this corresponds to universality and ultrahomogeneity of the standard construction. And then there is one more property I want to point out. So this is all that we know about this structure. So about these properties, I said for you, unique. So these properties, if I have any structure in my language, and the structure happens to have these two properties with respect to F, it is isomorphic with the structure that I constructed. So this these 2 points remember everything about the structure. There is another way of characterizing it by the so-called projective extension property. So projective extension property, if you remember this diagram that I had here when I constructed this generic sequence, projective extension property says the following thing, that if I go from F to A, I have these two diagrams, and these are, of course, structures coming from script F, and this is my limit. I can close this diagram like that by an epimorphism. So this is F. And this also, so this gives a different characterization of projective extension property. And essentially, what's happening in all these, say, homogeneity results that we want to prove, you take this projective extension property, you want to prove some homogeneity result, and when you analyze it on the combinatorial level, it turns out to be what you need. Normally you will run the so-called back and forth argument, going back to counter. So this is an argument that you have two linear dense orders without first point or last point, and they are countable, then they are isomorphic. This is an odd counter argument. You go this way and then back, and then so on. So you always run these back and forth arguments. There's nothing else You always run that. But the question is, can you run it? So when you analyze, if you can run it, whether or not you can run it, it boils down to some combinatorial question. And this combinatorial question usually is a strengthening some kind of souped-up version of this projective extension property. And this is what you, and then you work purely with the family F, essentially, the script family F, trying to prove this additional projective extension property. And then you prove a topological consequence. Okay, so this is this projective extension property. Let me just say, there's one. So what will happen is, so what happens in examples is, I have a well, let's call it a relevant compact space X, and then if the space is relevant enough, so nice enough, canonical enough means highly homogeneous, maybe universal in some way, then there will be a natural projective Freyset class. Natural in the sense that it will be given by nice combinatorial properties that we can work with. And then, so I can extract, I will be able to find or guess this natural projective Freyset class, and then the language will always contain a distinguished binary relation R. This relation R will live on all the structures in F, but, and it will turn out, normally it's not an equivalence relation on structures in F, but when you take the limit, from the properties of the limit, you will be able to check that it becomes an equivalence relation. So as you take this limit, R will be interpreted in the limit. And then by something special about the situation, it will turn out to be an equivalence relation. Well, so we have a counter set, this F, and an equivalence relation R on it. Well, you would have to divide. It's a compact equivalence relation. You divide, and if you chose things properly, you get X back. So you will get X. So you have a representation of X using this family of finite structures F. This representation will be, this situation will be such that, this is where often, this is something that is often very useful. You look at automorphism of F. So what is automorphism of F? F is a counter set. You look at homeomorphisms of this counter set that preserve the underlying structure, so the graph structure or the linear order structure, things like this. This gives you a group of transformation of this counter set with a topology. Well, the uniform convergence topology. If you now think about an automorphism of F, this automorphism of F in particular will preserve the relation R, because the relation R is part of the structure. So any element of odd F preserves this equivalence relation. Therefore, it is pushed down in X to a homeomorphism, because it preserves the equivalence relation, divide out by it, you get a homeomorphism of X. So you have a homomorphism, a continuous embedding, a continuous homomorphism from odd F to homeo of X. And you check that in all these situations, you are getting a dense subgroup. You are always getting a dense subgroup. This is not, so it has, homeo of X has a Polish topology on it, complete metrizable topology. Same odd F has a complete metrizable topology on it. But when you embed it into homeo of F, the topology inherited by odd F is weaker than the original one on it. So this is a property continuous embedding. This makes actually things easier, because odd F is much easier to work with. So this F is what I would call a pre-space for X. Okay, so then the topological problems are traded for combinatorial problems of the zero-dimensional space F and the family F. So now, what happens if it turns out that this is actually much more general than that? So what I said here, there is this word relevant and natural. If I have a relevant space, I'll get a natural class. If you don't care so much about natural, you can actually get every space this way. So this is a theorem of Panagiotopoulos, so this is a student of mine. So he showed that if you take any compact space, you can cook up projective Freyset family F with the properties from the previous slide. So that if you take the limit, this boldface F, it will have this natural equivalence relation R on it. You divide by it, and you get X. And odd F is homeomorphic, is embedded as a dense subset of homeo of F. But what you have to allow in the language, so I said that, so you have this R, there's a language. I said you have to go cut down to a subcategory. And this cutting down is done through a device called the dual relation symbols. So these are not, if you are familiar with, say, normal symbols in model theory, they bind tuples. So R holds of a tuple, say, less than in a linear order, tells me something about pairs. Right? So here one has to dualize it. So one has to ask what is the dual of a tuple. So a tuple is a function from a finite set to your structure. That's a tuple. So if you dualize, you have to reverse the R. So a dual tuple will be a function from your structure to a finite set. Your structure is topological, is a topological structure, so it has to be a continuous tuple. So a dual tuple is a function from your space to a finite set that's continuous. And your our relations talk about this sort of dual tuples. They say this dual tuple is in a relation, this dual tuple is not in a relation. This kind of relation symbols you have to involve here. So this is, it's essentially like working with partitions. So this, so I should say that this actually, inspiration came from dual Rampe theory. There's also in Rampe theory there's this duality. And so naturally when one tries to dualize so-called structural Rampe theorems, this is the relations one comes up with. And this is, turned out that they are relevant here as well. Well, one should say, okay, so this is great as it is, completely general, but if you just look at a concrete space, what you get from it, this class F, is not very natural. So it's not really a class that you are able to work with. But it's very nice to have this theorem because we covered everything. Okay, so what are, let me just go over examples of some relevant, what I would call relevant spaces here. So the spaces that we study using this method. So the pseudo-arc. So most people here probably know what pseudo-arc is, but let me still go through the motions. Maybe some people don't. So this is not, and I will not give a definition of it, so it's all good. So what I will give it as a property of the pseudo-arc that completely determines it, that comes from a theorem of Blind. So you look at compact subsets of the Hilbert cubes with the Vietoris topology. That's a compact space. Then you look at connected subsets of 0, 1 to the Hilbert cube that are connected and compact. So the script C is a subset of a K of 0, 1 to the n, and it's compact. It's Sierpinski's observation from the 30s, so it's compact. And then it turns out, so something quite stunning, and this was to me when I first saw it. So there exists a unique element in this C with the property that if I take all its copies, so there's a unique P in C, so that if I take all the homeomorphic copies of P, so P primes and P primes homeomorphism, this is a dense G delta subset of C. So topologically, almost every element of C is P. So notice that this property completely determines P, because if I had P1 and P2 of this sort, for P1 and P2, these sets would be dense G deltas. By Berg category theory, they would intersect, so they would have a copy, so they would be the same object. In any case, that's my pseudo. So another relevant space is the Lebesgue fund. This is what was also studied. I will not say much about it. So this is unique. So you look at the counter set times 0, 1. You glue together the counter set 0, 1. I'm a tourist here, so I'm not a topologist. I'm probably over-explaining some things, but the counter set times 0, 1, and I glue together the bottom layer, and then inside of, so there's a compact set. Inside of it, I find there's a unique up to homeomorphism compact subset. With the problem, with the property that if you take, so it's a compact subset, it's connected. If you look at the rays, the endpoints are dense. This is Lebesgue. Okay, then the Menger curve. So I'll just draw a picture. This is a one-dimensional analog of the counter set. So So I guess that's like self-explanatory here, right? You take the cube and you drill holes 1/9 of the cube, 1/9, 1/9, and then you do all the smaller cubes. And then mega compactor. So this is something that we would like to really get a better understanding of using this method, but we don't have that. So this is actually a beautiful family of higher dimensional compactors, starting with the counter set at 0 and at infinity, the Hilbert cube, and you've got, so mu1 was on the previous picture. For each dimension you have one like that. So this is a really nice thing. Somehow there is some connection between descriptive set theory, descriptive set theory and infinite dimensional topology. Descriptive set theories work on the counter set, mu0, and then there's this beautiful array of objects that are of the same type that connect mu0 with the Hilbert cube. And somehow the same properties often play an important role in descriptive set theory or in infinite dimensional topology. In any case, so this is our relevant object, but this is maybe for the future. So what are some, let me say some applications that were gotten in this method, and then I will do some illustration. So first some applications without going into details. So what we did initially with Erwin, so this was, initially with Erwin what we did, we found a new characterization of the pseudo-arc using projective homogeneity. So it was a long time ago when we first came up with this method. There's a, you see, I mentioned this, it is projective ultra-homogeneity of the pre-space. And then it immediately gives you a certain type of homogeneity of the pseudo-arc. It turned out this homogeneity characterized the pseudo-arc among trainable continua. So this was something nice to get. Then Oppenheim, for example, used this to find a homeomorphism of the pseudo-arc whose conjugacy classes are dense. The class is dense in the homeomorphism, in the group of all homeomorphisms. So this is something that was not known, right? So you look at homeomorphism group of the pseudo-arc, that's just a group. You find a homeomorphism there, so that you keep conjugating, you will get a dense subset. Then Bartoszowa and Kwiatkowska got the following result, also using this method, looking at the Lelek fan. So the homeomorphism group of the Lelek fan is totally disconnected, but it is generated by each open neighborhood of the identity. This is a bit, if you are familiar with, say, a little bit with locally compact group, this is an unexpected property, because for locally compact groups, if you are totally disconnected, you have arbitrarily small open subgroups. So for Polish groups, so-called Polish groups, so groups that are completely metrizable, separable, this was a problem from the Scottish book, whether you can get connected, totally disconnected groups that are generated by each open subgroup. This was solved some time ago, but then people asked, what about if you restrict yourself to homeomorphism groups of continua? Can you still get a counterexample? And it turned out that you can, for example, for the Lelek fan. So this is quite a recent result of Bartoszowa and Kwiatkowska. And then with Todor-Tsankov, we looked at this pre-pseudo-arc. So we have a pseudo-arc, we have this pre-space, and we found we established a generic homogeneity of this pre-pseudo-arc, and which gave a new proof of high homogeneity of the pseudo-arc, which we were happy about. So there are some problems still that are left. Maybe I will mention them here. So initially, this idea came up when trying to solve the following problem of Uspensky that remains still open. So the problem of Uspensky says the following thing: if you have a pseudo-arc, you pick a point in it, you look at all the homeomorphisms that fix this point, and then you ask, is this group extremely amenable, what they call extremely amenable, meaning if you take any continuous action of that group on a compact space, does it have a fixed point? So this is still not known. This normally extreme amenability connects, if it's true, connects with Ramsey theory through these Frey-Sess structures. And this is why this seemed relevant. Turned out, as far as we know, it cannot actually be applied. There is also a problem here. So high homogeneity, so we do get homogeneity between finite subsets, all possible homogeneity of the pseudo-arc, the ones that are true, among finite subsets, but we don't get them for subcontinuum. So this is still, we don't know how to use this method to get for subcontinuum. We cannot read the original paper here. Okay, so let me just illustrate how this method works. So on this concrete example of the member. So what do we do here? This is actually made one of the simpler examples. So you look at the binary relations. So your language will just contain one relation, R. And then what you will take for your class, so for each of these things, the pseudo-R, the lyric, you have to craft a class. So these classes are sometimes easier, sometimes more difficult. So for the Menger curve, you take all reflexive connected graphs. So what I mean by it is a finite graph. It's a symmetric relation, but we not only allow loops, we insist on loops. So every point has a loop. And we want these graphs to be connected. And then what are the morphisms? So these are simply all epimorphisms. So I take an epimorphism between two such graphs. And I take a subcategory of it, namely those that are preimages of connected sets are connected, or equivalent to preimages of points are connected. Right? So this is just finite class of finite graphs. And I restrict my morphisms to be these sort of morphisms. Okay, so this is my class. That's all that one needs to know about this. So this is a class actually studied by combinatorialists. So what happens is this one checks. This is just, it's all finite, right? So one checks that this is a projective Freise family. So the main thing is that this amalgamation property holds. And second, one checks that so it's the projective amalgamation holds. Therefore, I can take a limit of it. So there will be this counter set M with a relation R interpreted on it. So one takes this limit. There is this binary compact relation. It will be automatically symmetric because R was symmetric on all the structures. It will also be reflexive automatically, but it turns out that it's also transitive. So it turns out that in the limit, this relation is transitive. Therefore, it's an equivalence relation. So I can mod out. So when I mod out, it turns out this is the Menger curve. Notice that this relation on finite graphs is essentially never transitive, because if you these are connected graphs. If you transitivize, you get the whole graph in a single class. But what happens in the limit is the following thing. So why is this an equivalence relation in the limit? So what happens in the limit is, there's sort of, even though on each level you get connected structures, when you take the limit, there's a sort of a complete disintegration happens. So what happens is, for every point is of course connected to itself, and maybe it's not connected to anybody else, or there's a second possibility that the point is connected to itself and to a twin. And the twin is only connected back to the point and nothing else. So the points either come in pairs or are singletons. This is what happens, and one has to check it from the definition of Freise limit. Either singletons or doubletons. So a single point, the generic position is a single, so most points are singletons. And then, but there's uncountably many points that are common pairs. So the situation is a very simple example of that situation is, if you take the counter set, the usual counter set on the real line, look at the removed intervals, and make the equivalence relation on points that are endpoints of removed intervals, make them equivalent, and then all the other points that are not endpoints of intervals, just leave them alone. That's a compact equivalence relation. When you divide by it, you get the interval. So it's a very similar situation that happens here, except that the equivalence relation is much more complicated. So all the equivalence classes have 1 point or 2 points, but when you divide, you get the negative. Okay, so this is the situation. And then what we get, so what one now, let's say, the interesting thing, so for us actually, these objects that with these pre-spaces that we get are interesting in their own right. So this pre-Menger curve, actually, it's an interesting object from, for descriptive set theories. Same for this pre-pseudo-arc. So naturally, you would ask a question about this M1, how homogeneous it is. So mu1 is completely homogeneous. If I take endpoints, And the matching between them, I can extend it to a full homeomorphism of mu1. But as I said, I almost said, the pre-Menger curve cannot be completely homogeneous because you have two types of points. You have a point with that is a double tone and a singleton, and there will be no automorphism of M1 that maps a singleton to a double tone because it will not preserve the relation. So the situation here is more sort of mysterious for M1. But there is a general result, homogeneity results for finite subsets of M1. So what happens is, let's take two finite subsets of M1 and assume that they are saturated with respect to R, meaning that if I have K and I have something related by R, so this is this equivalence relation, to an element of K, this something is also in K. Same for L. So K and L are saturated. And assume I have an isomorphism between K and L. So I have a matching, so K and L are finite, matching between the points in K and L, but this matching respects the underlying model theoretic structure. So if I have a point in K mapped to a point in L, and the point in K has a twin, then the point in L also must have a twin, and they are also matched by this matching. Then every isomorphism like this extends to a full automorphism of M1. So we recover most of the homogeneity there, and then so the proof goes, as I said, through. I see. Became very talkative. So okay, let me just. So we get projected extension property. Strong version of the projected extension property is used here. Out of it, we get this Anderson's theorem as a corollary, that full homogeneity of mu1. I would be lying if I said we get it immediately. If you want to get it immediately, you would be in trouble. You notice that if I have, say, so what's happening here is, look, if I have M1 projects down to mu1, if I have finitely many points here, and the matching between these finitely many points, these pairs, I want to, sorry, I should have drawn it here, sorry. A matching, you would want to extend it to a homeomorphism. How would you do it? Well, you take pre-images in M1. You have a matching here, then you have a matching in M1. So if this matching extends to an automorphism of M1, which projects down to a homeomorphism of mu1, and you are done. The problem is that as you take the pre-images of these points, some of them will become double tones, some of them will become singletons. So even though here you have a matching, in M1 you will fail to have a matching in general. So there is a theorem that I'm hiding. You have to prove that each tuple of points in mu1 can be lifted to a tuple of singletons. Because singletons, as I said, these are points in general position, so you sort of have to jiggle a little bit the space, and you can get them to be singletons, and then if you do what I just said a moment ago, things will work out. Okay. So let me just very quickly go over this higher, and then you essentially cover the whole theory of mu1. You get, say, universality for one-dimensional compact spaces, things like this. You get as consequences of this representation. Okay. So I want to say that, say, this is a very this is normally what this is the price you pay, say, when you want to prove homogeneity results, say, for the pseudo-arc. The price you pay, it's much easier to prove homogeneity in these pre-spaces because it's all combinatorial. The problem is the homogeneity is false there. So you have to, only a remnant of the homogeneity, some sort of generic homogeneity falls there. So you have to guess what this generic homogeneity is, what types point. So say in the pseudo-arc, each point, the points have the same type. They can be, but if you go, you move it to the pre-pseudo-arc, points will have different types, not just singletons, doubletons. They have subtle differences. You have to recognize what these differences are and then take it into account when you prove homogeneity and then you prove some kind of transfer to mu1. But it's all normally quite doable. Okay. So what I want to talk a little bit about, say, these higher dimensional objects, simplexes. So what do you do, let's say, you want to do, say, homology theory for, if you want to tackle, say, higher dimensional Mengers for these pre-spaces. So these are spaces that don't contain any simplex or anything like this. So you have to know what the simplex is in the category of these projective Fraser limits. So how would you define a simplex there? Simplicial complex, this is the usual thing, downward closed family. So notice if I have any simplicial complex, I have the edge relation. So if I have a simplicial complex, I will have a distinguished relation, binary relation there that I need. So this is just 2 points are related if the edge is a face of the simplicial complex. So I look at simplicial maps, so this is as usual. And I will look at simply a combinatorial simplex. So this is power set of a finite set X minus the empty set. So this is the situation I want to consider. So I have simplicial complexes, and I'm really looking at this one here. And then I want to form a class. So what is? So I would like to have to know what a simplex is in the category of this projective Fraser limit. So what is my class? So by my I will take my class to be all the barycentric. So barycentric subdivisions, higher order of the simplex that I started with. But I view barycentric subdivision in this usual way, but it's combinatorial. So if I have a simplicial complex with barycentric subdivision, what are the vertices? Are old faces. Are the old faces. What are the new faces in the barycentric subdivision? These are families of faces linearly ordered by inclusion. So this is the usual combinatorial point of view of the barycentric subdivision. And I define a special kind of map. This is a selection map. So a selection map from a barycentric subdivision to the complex is just the simplest, set theoretically simplest map possible. So you take a simplicial, so you take a barycentric subdivision. You want so in beta, I want a vertex in beta A. So that's a face in A. So this little s is a face in A. I just pick a vertex in it. So I take in any way I want. So I call a map like this a selection map. So it turns out each selection map is a simplicial map from beta A to A. Is that clear what I want to do? So this is geometrically is actually quite simple maps. Set theoretically are just the only thing you can do. There's nothing else. Just pick a vertex on that. So my class S consists of barycentric subdivision of this fixed simplex that I start with. Higher and so as k goes up, I just keep applying barycentric subdivision. And my maps, I just look at maps coming from identity, close under composition, throw in the selection maps, this is the key ingredient, and close the class under barycentric subdivision. So if I have a morphism, I apply beta to it, it's still there. And so, as it turns out, this is a projective Fraser class. It turns out that I can take the limit of it. This R, this special relation R, when I take the limit, again, this integrates, not in double tones, but in fact, so it becomes an equivalence relation, so this R becomes an equivalence relation on the limit. Classes are no longer double tones or singletons, they go up to the dimension of the simplex, so but they are still finite, I can divide, and then when I divide, I get this geometric and dimensional simplex. So this is how you get simplexes here. If you now the problem with it, let me just I'll take 1 more minute. Is that okay?
1 more minute.
The problem with these maps is they are very rigid, so they are quite difficult to apply. These selection maps. But then the natural question, let me just skip this slide, I'll just say there's a natural, we define natural category theoretic closure operation on classes of morphisms. So this is something completely abstract. There's a very natural closure operation. So I take my selections and I want to compute its closure. These will be maps that I can still handle, and there will be as many of them as I can possibly get. And then we essentially get, in this closure, when I take the closure, these are precisely the simplicial maps whose geometric realizations are near homeomorphism. So this is a slight lie, but morally this theory is true. So I get quite, in disclosure, this is this math that I can still handle using the Fraser situation. I get essentially all near homeomorphisms. So this is actually quite flexible. And I'm done.
Are there any questions? If not, let's thank you. Oh, there's a question there.
This is very vague and maybe stupid. I'll apologize in advance. But set theoretics biologists have been using elementary submodels for 20 some odd years. You know, is this sort of maybe elementary submodels for continuum theory? Does it make sense? Or, I mean, it looks just the similarity is you're abstracting the properties rather than dealing with the nitty-gritty points, and then
yes. I don't think there is a direct connection. I mean, it comes from both comes from model theory.
Right.
I don't think there is a direct connection.
I don't know of any use of the elementary submodels to prove the theorem in continuum theory. I just wonder. I mean,
it would be nice to have it, but I don't see that. I don't see that.
Any other questions?
You mentioned applications to logic. Could you give us an example?
No, well, so they are not really applications to logic. So applications to logic so far are potential. So these structures that we construct are just interesting model theoretic structure, it seems to us. So the structure of pre-Menger or pre-pseudo-R. And then in logic there are natural descriptive set theory. People study automorphism groups of models. This gives new examples of automorphism group of models. So for example, say in dynamics, so this is what logicians study nowadays. So look at the automorphism group of the pre-pseudo-R and look at its dynamics. What is this universal minimal flow? Is it extremely amenable? What additional structure we need to put to make it extremely amenable? Things like this. So there was some work, for example, done in the pre-pseudo-R. It's known that this automorphic group is not only not extremely amenable, but its universal minimal flow is not metrizable. This follows from some anti-Ramsey theorem, and there is so there's things like that.
Anything else?
You talked about there are some compact spaces where you can get a projective Price-State class, which is ordinary relation. And then Aristoteles' more general theorem, you have the dual relation. Is there a precise characterization of when you can get away with ordinary?
No, it would be nice to have it, but no. There's some people in Italy who look at it. They talk with me, but there's no concrete result. They just have examples, but there's no even conjectural line.
Other questions? And let's thank our speaker again. I believe now it's coffee break.